Look around any major city today. Every smartphone, every electric vehicle, every towering skyscraper made of glass and steel exists for one reason. We figured out how to pull the exact right pieces out of the dirt. The Earth's crust is far from uniform. It is a complex mosaic of rocks and the specific, naturally occurring chemical formations that build them, which we call minerals. Not all minerals are built the same. We generally divide them into two massive categories, metallic and non-metallic. The metallic group gets even more specific. If a metal contains iron, like the ores we use to forge steel, it's classified as a ferrous mineral. If it doesn't contain iron, like gold, silver, or copper, it falls into the non-ferrous category. Knowing the chemical makeup of a resource is helpful, but none of these materials have real economic value until we can physically locate them and dig them out of the ground. That process of extraction is mining. We target specific rocks with high concentrations of valuable minerals, known as ores. Once the valuable material is separated, the leftover rock is simply discarded as tailing. How we get to that ore depends entirely on where it's hiding. If a mineral is sitting near the surface, we use open pit mining or quarrying, where massive machines literally scrape away the top layers of the earth. But if a solid resource is buried deep underground, a surface pit won't work. Miners have to dig deep vertical holes and tunnels, a method known as shaft mining, just to reach the deposit. Liquids and gases require an entirely different approach. To extract resources like mineral oil or natural gas, we construct towering derricks to drill deep wells and bore down into the subterranean pockets holding them. Between the sprawling open pits, the deep underground shafts, and the massive drilling rigs, it takes a staggering amount of mechanical force to pry these resources loose. The Earth does not give up its wealth easily. Even with advanced mining technology, a nation might have nothing beneath its feet. Mineral distribution is dictated by ancient geological processes, completely ignoring modern political borders. This map details the global distribution of major minerals. Africa holds a significant portion of the world's gold and diamonds, while Australia dominates bauxite. But for heavy manufacturing, production shifts to Asia. China and India are the largest producers of iron ore. This map details India's mineral concentration. The eastern states are the industrial heart, holding vast coal and high-grade iron reserves. Out west, Rajasthan holds major copper deposits, while southern Karnataka harbors gold. India is also the largest producer of mica. This geological lottery means a nation's industrial starting point is dictated by the raw materials it can access at home. While trade moves these goods globally, the underlying wealth is fixed by the earth itself. Building modern infrastructure is only half the equation. Once built, cities must be powered, and for centuries we've relied on conventional energy resources to keep the lights on. At the most basic level, millions in rural areas still rely on firewood for domestic heating and cooking, though burning it causes significant air pollution. On an industrial scale, coal is burned to generate thermal energy. Meanwhile, petroleum is extracted and refined to drive global transport and manufacturing. The issue is how fast we are burning through them. Developed countries make up only 16% of the population, yet consume a disproportionate share of the planet's finite energy reserves. This chart shows the extreme difference between resource formation and human consumption. That long, flat line represents the millions of years it took for organic remains to compress into coal and petroleum. That sharp vertical spike is humanity exhausting them in mere centuries. We are drawing down a finite bank account. Once these fossil fuels are gone, the Earth cannot replenish them on any timeline that matters to human civilization, leaving us facing an inevitable energy cliff. Because every mineral and fossil fuel we extract is non-renewable, our immediate defense against resource exhaustion is strategic conservation. This happens in three ways: recycling discarded metals like copper and aluminum so they can be reused, optimizing our extraction processes to avoid wasting raw material, and developing biodegradable substitutes to replace plastics and synthetic chemicals. But making existing supplies slightly longer doesn't change the ultimate outcome. Conservation is a necessary bridge, but it isn't a permanent solution to our energy needs. To secure a long-term future, we have to pivot away from digging finite resources out of the ground and start capturing the infinite flows of non-conventional energy around us. We can trap sunlight using photovoltaic cells to generate electricity. In tropical regions, and specifically in Indian states like Gujarat and Rajasthan, the potential for solar generation is vast and entirely inexhaustible. We can also tap into the wind. By placing turbines in coastal regions and open plains where air currents are constant, we generate steady, low-cost electricity without polluting the atmosphere. We can use the kinetic force of falling water. In hydroelectric systems, river or rainwater rushing through a dam physically spins generator blades to create electricity, a renewable resource we can use indefinitely. This diagram shows how we can even turn our own waste into fuel. By feeding organic matter, like agricultural and kitchen waste, into an underground digester tank, we can capture the resulting biogas to use for cooking and electricity. Our past was built on draining finite reserves, but our continued progress relies entirely on harnessing these infinite flows. Because ultimately, energy intelligently saved and sustainably sourced is the only energy that will last.